So good evening, everyone. We are Team 26, and today we are excited to present Dexterity, a beginner-friendly programming language we designed as part of the SER 502 course on programming languages and paradigms. I am Annie Susan, and along with Sricharan, Pooja, and Gokul, we have worked together on this language from syntax design all the way to runtime execution. So moving on to the next slide. So here's a quick look at what we'll be covering today. We'll start with an introduction to language, then walk you through its syntax and grammar. From there, we will explain how we built the lexical analyzer and parser, how we generated intermediate code, and finally, how our runtime interpreter executes that code. So, over to the next slide. So Dexterity is a simple and intuitive programming language. It was developed and tested on Windows, and we used Java and Antler 409 as our core tools. The language supports basic data types like int, float, bool, and string, and provides essential control structures like if, else, while, for loops, and even ternary operator. Our goal was to make the syntax easy to read and use, especially for beginners, while still being expressive enough to write meaningful programs. Coming to the syntax. So now let's take a look at the basic syntax. So variable declarations in Dexterity follow the format like that you're already familiar with. Uh, the data type of the variable and the name of the variable and the value uh, which you wanted to assign to the variable. And when coming to the conditionals, it also has the familiar structure. So it starts with the if keyword followed by the parenthesis. Inside that, you can go, you can just define the condition and then what you have to do. And for loops, here is a classic for loop syntax. So you'll notice the style is very similar to languages like C or Java. That's intentional because we wanted to lower the learning curve. So moving on to the next slide, which is the variables. So variables in Dexterity must be declared with the type before they are used. Supported types include like int, float, bool, and string. Once declared, they can be initialized with a value or assigned one later. Behind the scenes, like every variable is stored in a symbol table, and the interpreter ensures type consistency throughout the execution. Okay, next the conditionals. So Dexterity supports both traditional if-else statement and ternary operators for conditional logic. A simple if-else looks like this. If followed by the condition and then inside the parenthesis, you have to specify uh, what you have to do if the condition turns out to be true. And we also support chaining multiple else if blocks, and for concise conditions, the ternary operator is supported as well. So this keeps the language flexible and expressive. Followed by the loops. So we have implemented both for loops and while loops in Dexterity. A typical for loop includes initialization, condition, and update inside parentheses, just like in Java. And our while loop checks the condition at the start of each iteration. These constructs are powerful for building a repetitive task like summing numbers or iterating over counters. So over to the next slide, the grammar. So now moving to the grammar of the language, we defined our grammar in Antler using a .g4 file. The entry rule is something like this: like program gives a list of statements. The key grammar rules includes declaration statement, which gives the type, ID, and the expression. followed by the assignment statement and then the expression and the control statement. So these rules let us support variable declarations, expressions, loops, and conditionals in a structured way. The grammar is the backbone of our parser and drives the generation of our abstract tree. So what is the next slide, which will be taken my way, friend? Thank you.
Hi, my name is Pooja, and in this part of the presentation, I'll walk you through lexical analysis and parsing process in our Dexterity programming language, covering through slides 12 from slides 12 through 17. We used ANTLR4 to define Dexterity's grammar in a file called dexterity.g4. ANTLR automatically generates a lexer and a parser based on this grammar. The lexer performs lexical analysis, breaking the source code into tokens such as keywords, identifiers, operators, and literals. It also ignores white space and comments. Once tokens are created, they're passed to the parser, which applies grammar rules to build a parse tree. This tree is the structural foundation of our program, allowing us to understand the code semantics before generating intermediate instructions. In this slide, we show how the lexer and parser are set up in compiler.java. We first convert the source file into a character stream and pass it into the lexer. The resulting tokens are sent to the parser, which runs the top-level program rule. This rule captures the overall structure of a Dexterity program, triggering other rules such as declarations, assignments, and print statements. Here, we use ANTLR's two-string tree parser method to generate and print the parse tree. The output is in a bracketed format, giving us a clear view of how each code element is parsed. This is useful for verifying that the grammar rules are working as intended. To demonstrate this, we use the simple dexterity program, declaring variables a and b, assigning them values, and printing arithmetic operations like a plus b and a minus b. This code serves as a clean test case to validate expression parsing. This is the full parse tree output generated from that file. The tree begins with the program node followed by statement nodes. Each print statement includes a nested expression subtree showing the correct order of expression and syntax mapping. And finally, we have a screenshot of the parse tree output printed by ANTLR. It ends with an EOF token confirming the file was parsed successfully. This verified tree is then used to build our abstract syntax tree and intermediate instructions. Thank you.
Okay, so hi everyone, I'm Gokul Selvan and I'm presenting on behalf of Team Tech 26, Dexterity. Today I'll be talking about one of the core components of a language implementation, intermediate code generation, which you will find on pages 18 to 21 of our report. So far we have discussed how a language parses and understands the code. Now let's talk about what happens after parsing, how Dexterity turns that into understanding something executable. So once you've built the abstract and syntax tree, the next step is to generate intermediate code. This code doesn't run on a real CPU, but it behaves like it would using a stack-based model. So we created a set of simple instructions like declare, push, store, load, add, sub, mul, div, and print. These are enough to perform arithmetic logic and control flow, all without needing to compile to machine code or bytecode. This the idea is to keep things light, clear, and beginner friendly, staying true to what Dexterity is actually meant for. So to make this more concrete, let's look at how a piece of code becomes intermediate instructions. So take this line for example, int a is equal to 10. We break it down into declare int a, push int 10, and store a. Or take this line, print a plus b, so that becomes load a, load b, add, print. So we do this by traversing the AST in post order, which means we evaluate sub expressions first, then combine them. It's efficient and ensures everything is handled in the correct order. Now, inside the Java interpreter, each grammar rule in Dexterity has a corresponding handler method. For instance, when the parser recognizes an addition, we call the handle add method, and here's what it does. It pops two values of the operand stack, adds them, and pushes the results back. This approach lets us simulate real arithmetic operations without needing a full compiler backend. It's simple, but it works beautifully. And finally, this page shows the actual set of instructions we generated for the arithmetic text code example. So we start with variable declarations and store their values, then perform arithmetic operations, and finally we print the results. Just like how a mini virtual machine would execute each line one at a time. So what you see here is the bridge between high-level dexterity code and low-level execution logic, all happening through clean stack-based intermediate code. And that wraps up my part of the presentation. Thanks. Thanks so much for listening.
Hello everyone, I'm Sri Charan. Now I'll explain the runtime environment of our language. This is where our code actually comes to life. So let's go over it. Our runtime interpreter is written entirely in Java, creating a lightweight execution environment for Dexterity programs. After the lexical analysis and parsing phases generate our intermediate code, the interpreter takes over to execute this code line by line. The interpreter operates on three key components: a program counter to track execution position, an operand stack for managing data values, and an instruction list containing the commands to execute. This stack based execution model is both elegant and efficient, allowing us to process our operations in a predictable sequence. When executing a dexterity program, the runtime environment processes each instruction by popping operands from the stack, performing the required operation, and pushing results back. For example, in arithmetic operations like addition, the interpreter pops two values, adds them together, and pushes the result back onto the stack. One safety feature we've implemented is an instruction limit that halts execution after 1,000 instructions, preventing infinite loops for consuming system resources. This makes Dexterity ideal for educational environments. Our variable handling is equally straightforward. We maintain a simple table that maps variable names to their values, and variable types map to track data types. When variables are declared, they are automatically initialized with sensible default values. Integer starts at 0, floats at zero point 0, booleans as false, and string as empty. The arithmetic and logical operations in our runtime demonstrate how we've implemented type handling. For example, our addition operation can handle both numeric addition and string concatenation, detecting the operand types and choosing the appropriate behavior. As you saw in our demonstration, the runtime correctly executes our arithmetic.dex example, calculating and displaying sums, differences, products, and quotients precisely as intended. To conclude, Dexterity represents our successful implementation of a complete programming language pipeline, from lexical analysis through parsing to runtime execution. It's a beginner-friendly language built on Java and Antler 4, covering all the fundamentals aspects of programming language: lexical analysis, parsing, intermediate code generation, and runtime execution. Dexterity supports all the basic programming constructs include variables, arithmetics, logic, conditionals, and loops. While simple, while simple, it demonstrates the core principles of language design and implementation, making it an excellent educational tool. The syntax is intuitive, the execution model is transparent, and the entire system provides clear feedback at each stage of execution. Our project not only met the course requirements but gave us valuable insights into how programming languages work under the hood. Thank you for your attention.